session A1, battery and geoenergy. And let me introduce our first speaker, the keynote speaker, Professor Edouard Asselin from University of British Columbia. And he's going to talk about mineral battery today.
Okay, thanks for the introduction. So as he said, my name is Zed, and most of the technical work that's in this presentation was done by my PhD student who just graduated a couple months ago, Kashif. So what I'm going to talk about today is the use of minerals in battery-like systems. The reason we looked at this is most of my research is in extractive metallurgy, so taking metals out of ores and minerals. And it occurred to me a number of years ago at a conference that one of the minerals in particular that's important for copper could be used both for oxidation and for reduction, or we could oxidize it and reduce it. And I thought that we might be able to use that in a battery setting. So what I'm going to do is develop that idea for you, and then we'll show you some results near the end. Oh yeah, this isn't working. So we're going to talk about energy use at off-grid sites, in particular in Canada, not so many in the States. Copper production, energy use and extraction, and the reason why some people are saying it's going to become scarce. And then we'll talk about zinc, because the particular battery I've looked at here is a copper zinc battery. So the production of zinc, energy use and the recovery of zinc, particularly the electrowinning step, so the step where we take zinc out of liquid and make a metal. And then incentivizing the use of renewables at mine sites by combining, sorry, this should say 2 and 3 in a battery-like setup. So, energy use at mining and remote communities. So on the left, we have a table that shows the electrical energy production by country in the world in 2016, and you can see that in Canada, we generate about 3% of the world's total energy. We're lucky enough that about 60% of that energy is generated through renewable means, through hydroelectricity, and then another 7% through solar, etc. We do, however, have quite a bit of coal and oil and others, which would include, of course, diesel. So generally, it's a pretty good energy profile, but we do have some exceptions. So as you all know, Canada is a large country, and there are over 200 off-grid communities in Canada, of which 96% of these off-grid communities use fossil fuel power, so diesel gensets. And you can see some of those communities here on the map in these red dots. There are also over 1,000 mines in Canada of various different sorts, and about 32, give or take, are off-grid mines. So they rely entirely on power from, again, diesel gensets typically. And most of these remote communities, I should say, also don't have access to natural gas. So everything is powered by diesel. The communities that are located within 100 kilometers of a copper zinc mine are highlighted here. So these are off-grid communities that are close to copper and zinc mines. And just to give you an idea of the scale of the issue, off-grid power demand for mining, so just mining operations, so these 32 mine operations that are off-grid in Canada, is about 660 megawatts. So to give you a comparison, the city of Boston in 2015 used 3,500 megawatts. So these are 32 relatively small mines, probably housing on the order of 100 to 200 people each, so fairly small, consuming tons of power. The main power draw for that in mining is crushing rock, which is extremely inefficient. Here's a picture of a diesel genset at a mine. I've been in mines where they have very, very large gensets, so the generator might be half or 3/4 the size of this room. At some of these mines, the average production at copper mines in Canada that are off-grid is about 35,000 tons of ore, or concentrate, I should say, per day. So you dig the ore out of the ground, and then you concentrate that into something that is more pure in the metal, typically around 15% metal, 15-20%. So we're treating 35,000 tons per day of concentrate, which means that the ore treatment is even higher. The energy cost for these copper mines is about $67 per ton of concentrate, and per pound of copper produced is about 16 cents or 15 cents, give or take. So this is a quote from a study done by Natural Resources Canada. So for the 9 mines that they studied, the total expenditures were $228 million for energy. The most heavily used fuels were diesel at the off-grid sites and electricity at sites that had power. So this amount of diesel is about 1,500 gigawatt hours, so similar to the amount of electricity that was consumed. So large numbers. So now we'll move into copper, which is the main reason I looked at this particular battery setup. And I want to take a step back to look at how much copper we produce worldwide. So we have, fortunately, data going back to the 1850s. This was compiled by a French economist in 2014, and I've added to it since. So these red lines are my data, or I should say internationally collected data that I've put on this graph. And you can see that from 1850 to about 2013, we produced 622 million tons of copper globally. In the next 25 years, we'll produce 640 million tons. So that's a lot of copper in a very short amount of time. And of course, because of this 2.8% growth rate in consumption, we anticipate producing another 635 million tons in the next 15 years. So there are no metals. Copper is the only metal that has this trajectory, and it's had this trajectory for at least 150 years. The reason is that copper is used in electronics and buildings and everything we make as a society, so it tends to follow population growth. So where is copper on the planet, and how do we talk about it in terms of how much we have? There were 2 sort of landmark studies done on this. The most important one is probably this one by the United States Geological Survey in 2013, which says that we have a reserve of about 700 million tons of copper. So that means that it's technically, economically, and legally extractable. So they have permits, or they have a likelihood of getting a permit to extract the copper. If we look at the resource, this is a larger pile of copper. This is about 2,100 million tons of copper. This is where economic extraction is feasible now or in the future, but where we don't have any legal permits or anything like that. And then there's this broad category under here called undiscovered resource, which is believed to exist or surmised from theory. And the number there is about 4,400 million tons. So if we accept these numbers, with the reserve, what we can extract today, we have 35 years of resource of copper. Of reserve, and 70 years of resource. And if we accept this number, which is highly uncertain, we may have another 200 years, give or take. So adding this all up, we have potentially 300 years of copper at current consumption rates. I just wanted to highlight this. This amount, just to give you an idea of the size, would represent a cube 600 meters by 600 meters by 600 meters. So it's a very large cube of copper. So if you accept that we're not going to run out of copper, the main issue that we do have, unfortunately, is that the grade of copper is declining. So the amount of copper per amount of gangue mineral or rock that is of no interest to us. And this has direct implications on energy. So typically, right now, the world copper grade is 6 kilograms of copper in 994 kilograms of waste. And most of that copper is mineralized as this particular mineral, which is called chalcopyrite. There's the formula. About 80 to 90, maybe as much as 93% of the world's copper is mineralized this way. And the combination of this low-grade issue, this little amount of copper in a bunch of waste, plus the main processing route, which I'll talk about in a second, gives us a very high energy demand, which is the issue that we're trying to address in this research, or at least partially address. So to give you an idea of the copper grade going back through the years, there is historical data for copper grade going back to 1900. So this is the amount of copper that was taken out of the ground per amount of waste rock. As a percentage is what is shown here. You can see that there's a definite trend downwards, and they're predicting that the data will go down to very low copper grades, and we have data from across the world, including from the United States. So right now we're sitting at about 0.6% copper in most of the ores that are mined worldwide. So the implication in terms of energy is shown on the next slide. So this is the embodied energy in copper. This has been studied many times over the years, and you'll find all sorts of different data sets for this. This particular set of data comes from these two studies, which offer a review, if you will, of the data and which present similar data. So that's why I've shown this. You may find other data in other literature that shows lower embodied energies. To give you a point of comparison, diesel has a calorific value of about 45 or 46 megajoules per kilogram. So these numbers are high, right? So if you think about it, what that means is that we're expending a lot of energy to extract copper, and most of that, a lot more energy than what is available in the fuel, and we put that into the copper. So it's a very, very energy inefficient process. So let's look at it from the perspective of cost. Let's imagine that you're operating a mine and that you have access to electrical power. Okay, so we're going to follow this top line, and I'll tell you what the difference between the top and the bottom line is. Basically, it's that the top line is processed in one way, which is kind of the least efficient method, and the bottom line is the most efficient method of extracting copper. So if we use the least efficient processing method available, then we can break even with the cost of electricity if we treat copper ores that have 1.5% copper, which is already well above, more than double what today's world average is. So in other words, you pay more in electricity than the value of the copper. If we go along the bottom line, which is a slightly more efficient route, you still don't do so well, but it's at least better. So it's 0.7% copper, which is the cutoff grade for equal amount of energy put into the material in terms of cost. There are a whole bunch of other constraints around extracting copper. Increasing water use as the ore grade goes down, increasing waste that you have to deal with. You have to put the waste somewhere. And of course, greenhouse gas emissions, which are associated with the increased energy use. So the two methods I referred to, low efficiency, high efficiency, are shown here. I've chosen a particularly bad picture on the left here. This is Sudbury, Ontario, Canada, which is a large mining district. This is a picture from the 1960s. It doesn't look like that anymore. It's currently much nicer. The plant is still there. It's still emitting smoke, but stuff is more green now. They've done a lot of work to make the process better. But 80% of the world's copper is currently produced via smelting, which is essentially scaled-up Bronze Age technology. Not much has changed in this world over the last few centuries. On the other hand, the most efficient method is heap leaching, which consists of just taking ore, piling it into heaps, which you see here on the left, and putting acid through the heaps, dissolving the copper, which you see here because of the blue color. This is the acid coming down the heap and coming into these gutters, and then going into a plant to recover the copper from the solution. You can imagine this is a fairly low-cost way of doing things, fairly energy efficient, but it's unfortunately only valuable or only applicable for copper oxides, which are being depleted. As I said earlier, 80 to 90% of the world's copper exists in this form. We cannot use this process for this mineral currently. So there are technological limitations. As a result of this discrepancy, for many years, at least 60 now, people have been engaged in trying to use this process for this mineral. And so the reactions have been studied quite a bit, and these are the sorts of reactions that come into the battery, which we'll talk about in a few minutes. So this extraction of copper from chalcopyrite using wet methods is called the hydrometallurgical extraction of copper. And if we start with the mineral, one of its particular properties or interesting properties is that we can oxidize it, and the reaction is something like this, where the copper goes into solution and the iron goes into solution. Or we can reduce it, where we make what's called chalcocite, and then that reduced species can then further be oxidized if we want to make covellite and maybe copper too. So this reaction here on the top, this product here forms a barrier, kind of like an oxide on a metal, and it slows down the process to such an extent that it becomes uneconomic under most conditions. To do it effectively, you have to use high temperatures and high pressures and pressure vessels, etc., which are uninteresting economically. And there are a whole bunch of other reasons why you wouldn't want to do that. So if I summarize for copper then, what I can say from what we've just talked about is that copper consumption is increasing rapidly. The grades are decreasing. There are environmental and economic constraints related to the different production methods, and technological limitations, again, with these two production routes. Only two processing routes exist, and each one has challenges. So as a result of these things, or these facts, some are predicting decreased copper production and associated scarcity. So there was an article in Scientific American which shows you what we expect. So some people are predicting that as soon as about 2040-ish, we will reach peak copper production. Now, there have been predictions for peak oil, which have not come true, but certainly in terms of copper, there are serious people estimating that we will have a problem with copper. One of the issues in this case is that there are no acceptable substitutes for copper. Sorry, what does the 3 mean? 3 minutes left? I thought I had 40 minutes. Sorry, I can do 3 minutes, but whoa. All right. So I have another 15 or so. All right. So that's copper. Now, quickly on zinc. The resource is not so stressed. These are the production levels for zinc. They've come down a lot recently. Mostly zinc is used for galvanizing. China's economy is slowing substantially. And as a result of that, we see a less demand for galvanized steel. Global zinc reserves are about 18 years at 2017 production. The resource is about 152 years. And unlike copper, there are many substitutes for zinc. So it's not such an issue in terms of needing to produce it. On the other hand, when we look at the energy embodied in zinc, a good quarter of the energy that goes into making zinc is in the one process called electrowinning. So basically, zinc ore is either roasted or oxidized in an autoclave. The zinc reports to a solution phase, so it's liquid. And then the zinc is electro-won out of the liquid as a metal. That's the main route we make zinc. 94% of the world's zinc is made that way. And this amount of energy is substantial in terms of the total energy that goes into zinc production. So for years, again, people have been trying to reduce the amount of energy going towards this, mostly for economic reasons. So this is a breakdown of the electrowinning process. So at the cathode, we have zinc in solution becoming zinc metal. Here's the potential for that. At the anode, we have oxygen evolution from water. There's a little schematic of what it should look like. The theoretical or thermodynamic cell potential is this minus this, which is 2 volts. And the specific energy is 1.6 kilowatt hours per kilogram. But because of losses at the anode and the cathode, and because of cell hardware losses, we end up with an actual cell potential of 3.3 volts. So we add these losses up to this 2, we get about 3.3, which means that the energy consumption is substantially higher, about double than what it should be, 3 kilowatt hours per kilogram. So people have been trying to reduce this for many years using different techniques, and I'll show you one that is applicable in the case of the battery. I also wanted to show you how large these processes are, the scale of them. So this is a cell house. You can't see terribly well because of these lights. The cell house at Trail BC for the Tech Corporation. Each one of these banks of cells contains 100 cathodes and 101 anodes. And there are literally thousands of anodes and cathodes in here. You can see them here harvesting the cathodes, and then the zinc would be stripped off those cathodes. So these are large industrial processes, several football fields in size, managed very, very carefully. And so it wouldn't be impossible to use such a setup in a battery-type setup. Here's another picture. This is from the Canadian electrolytic zinc cell house near Montreal. You can see the anodes are the kind of gray-colored, and in between them are the darker cathodes. Here's the cathodes being taken out. You can see the zinc deposited, and this is an anode which has got manganese dioxide mud on it. All right, so zinc production is also increasing rapidly. And the single most energy intensive process in zinc recovery is this final electrowinning step. So it occurred to me that we could combine these two processes to make a battery and use the minerals, particularly the copper minerals, for something other than just making copper. What if we could use them to store energy and make copper? So this is basically what we have. We have copper extraction. We're at a positive electrode. We can oxidize chalcopyrite and make copper 2, which we can then recover and sell. And at the negative electrode, we reduce zinc from a solution of zinc sulfate to make zinc metal. And here's what happens during charging. Copper leaches in zinc deposits. And during discharge, part of the energy can be retrieved at the expense, of course, of some zinc dissolution. The point of this slide was just to show you that copper-zinc mines are common. So this is a current operating mine in the province of Manitoba. Just to give you an idea of the size, there are 5 billion tons of ore containing this much copper and zinc. Another one at Kidd Creek near Timmins in Ontario has 10 million tons of ore grading 2% copper, 5% zinc. So copper-zinc mines are very common, and they are large mines. So schematically, what we had in mind was we used some sort of current collector. We put the mineral into an anodic cell. And then on the other side, across the membrane, we have a current collector which is in touch with the zinc sulfate system. And then we discharge this just like a battery. And in this case, of course, we have losses. And we hope that most of those losses are due to copper extraction at the anode, so that the discharge energy is equal to the charge energy minus the potential that's used in extracting copper, which, of course, is desirable because we can monetize that copper. So here's another schematic of the charging process. So we have zinc deposition to make zinc metal at the negative electrode. We have chalcopyrite oxidation to make copper 2 and iron 2 at the positive electrode. We may have some tanks where we can take out copper 2 for recovery. Here is the possible reactions. So of course we may get a little bit of hydrogen evolution in this cell. And of course we're going to have copper oxidation on the right-hand side. And then during discharge, we would have copper reduction on the positive side and zinc oxidation back into solution on the negative side. And we'd have a whole series of pseudocapacitive reactions, including the sulfide-disulfide couple interacting here, perhaps proton adsorption onto any activated carbon that we add into the system, and also copper 2, copper 1 exchange if that takes place. So now we'll move into the experimental setup. So briefly, this is what it looked like in the lab. So here's the cell with the chalcopyrite in contact with activated carbon and the zinc side. This is the setup, so a bunch of seals, gaskets, and membranes made out of basically Teflon and carbon current collectors. We used a syringe to pump the slurry into the chalcopyrite side, and of course these are all the hookups for the various electrochemical apparatus. And this is the peristaltic pump to have the zinc solution flow through. I just wanted to show you what the mineral concentrate looked like. So we did start off with synthesizing pure chalcopyrite. And then later on, what I'm showing you here are results from using a mineral concentrate. So this is what went into the positive side of the battery. So it consists mostly of pyrite, covellite, and then chalcopyrite, about 30%. And then a whole bunch of other stuff that was in there that was unwanted but is typical of a mineral concentrate. And that's what the morphology is. So first we measured what the theoretical cell potential was, or what it was when the system wasn't coupled together. It was about 1.2 volts as expected, and then we had losses in the system of about 0.3 volts, or just under 0.3 volts. So that's what I'm showing here. Once the system was put together, it had an operating potential of about 1 volt. We did cyclic performance testing of the battery. So you can see that the first charge regime, which is up here at 1 Coulomb, the specific capacity goes down as we charge the battery more. On the discharge side, the same thing. As we discharge it more often or cycle it more often, the discharge capacity or specific capacity goes down substantially. And this here is the energy efficiency on the right. And you can see that the energy efficiency is not particularly good, about 60% Coulombic efficiency and 40% energy efficiency. And the specific capacity, of course, is decreasing as the amount of cycles go up. So this is expected because the mineral is actually dissolving. So we're having losses associated with the mineral in the anode dissolving and copper being put into solution. This puts the two together. You can't really see with the lighting in here, but on the left-hand side, we have solution coming out of the analyte, which has got copper on it, and it's meant to show that it's getting paler blue in color, so more copper is getting into solution. We could calculate the copper extraction to a maximum of 23% after 100 cycles. And this is the copper extraction as a function of time, giving you an idea of how long we cycled this for. So just to give you an idea of the specific capacities for lithium-ion batteries, which most of you probably know by heart, it's in the range of 70, maybe up to 300 watt-hours per kilogram. So this is not particularly good. So here's the zinc being deposited. That's a SEM micrograph of the zinc surface. That's typical of what you would expect in an industrial process. And then here we have copper in solution. What's interesting about this system is it decreases the voltage for zinc deposition. So remember previously I had said that the voltage was around 3.3 volts. Now with this system, because we're oxidizing chalcopyrite at the anode, we have a voltage cell potential rather of about 1.6 to 1.8 volts, which means that the specific energy has decreased substantially for making zinc, which is also an advantage to this system. So I thought I'd quickly describe an example. This particular mine is a copper mine. It's in Princeton, British Columbia, which is in the interior of the province. It has 424 million tons of copper. It's producing 45,000 tons of concentrate per day, expected to do that for 26 years. It uses about 82 megawatts of power. So if we apply a 1 megawatt wind turbine with a number of assumptions, of course, just to give you an idea of the size of the battery we would require at the performance that we currently have. The total energy stored by this trifunctional battery, we call it, would be 526 megawatt hours, of course, in a year. And the amount of mineral concentrate that we'd have to load into each of the cells would be 718 tons in a year. And you would need 780 of these cells, which is not totally out of the realm of possibility given what we're used to dealing with in this industry. So the installation of a 1 megawatt of renewable energy, for example, a wind turbine in conjunction with this battery, at this site would give us the ability to store 526 megawatt hours in this battery, partially reduce the diesel utilization, and decrease CO2 emissions by about 1,500 tons per year, and extract 6,500 tons of copper per year, which are valued at today's price of at $38 million per year in copper revenue. So the idea is that no, mine sites don't want to pay for renewables. They don't want to build batteries. But if they can extract some value out of the battery, it may incentivize the adoption of renewables. And then finally, what does this look like? So we have this mineral concentrate, which is made by the mine. It gets shipped into these battery units. We have the renewables, which of course put power into the battery. Out of this system comes copper and iron. We have a solvent extraction, electrowinning. This is turnkey technology to make copper. And then the depleted acid solution goes back into the system. The mineral concentrate, which has been run for 100 cycles, for example, goes back into the pile and shipped out for sale. No harm done to the concentrate. So in summary, we've presented this trifunctional battery. There are irreversible reactions which are always unwanted in conventional batteries but are desirable in this particular battery system. We can simultaneously extract copper and deposit zinc. which allows for some flexibility in installation at various different types of mine sites. We can store initially 380 watt hours per kilogram, but this decreases to 50 over 15 cycles. The coulombic and energy efficiencies are fairly low, but that's due to copper extraction, and the revenue might incentivize renewables installation. Now, I thought I'd also talk about the limitations. These are only some of them. The economics of this system have not been studied in depth. The long-term performance of a large-scale battery has not been looked at, and one issue would be the membrane performance over the long term. This is likely a niche application for copper zinc, but the performance of the battery with gangue materials such as pyrite, which are typically unwanted iron sulfide minerals, is actually interesting, and we're continuing to look at that. And the system studied here is definitely a compromise. It's neither good for copper extraction nor good as a battery. So you have to compromise on both ends to want to use this system. Finally, I'd like to acknowledge, so my student was funded partially by the University of the Punjab. Of course, UBC had some scholarship money, and the Natural Sciences and Engineering Research Council of Canada. Thank you for your attention.
Great talk. So, any questions from the audience? Another question. So, for your battery, do you have any requirement for morphology of the copper side when you construct the battery, or it's just a copper foil?
So on the copper side, you put in particles, right? So concentrate, and typically they have a size range of 75 to 200 micrometers. So that's what we tested.
So you need particle.
You need particles, yeah, for now.
Any question?
Now, I should say, in this system, you would need particles. But if you were making a battery out of chalcopyrite, which I've seen some people are studying now in lithium-ion battery setups, you could make a slab of chalcopyrite. Sure. That's a difficult thing to do, though. To make a pure slab, yeah.
Other questions? No? Let's thank our speaker again.
Okay, thank you.
Okay.